So we take attendance first. Okay. Hopefully quiz tomorrow will help you a bit, prepare better for the test. Okay. You have chapter 3 and chapter 4. When I see the question, the one that is difficult is chapter 3. Okay. No, challenging lah. Question 3, okay. No, chapter 3. When I already see the question. And the hint for the quiz is actually no, the hint for the test 2 is actually uniform quantization, right? Uh, that was covered during my class, right? The one that covered during recording is non-uniform, right? So those that come during my class. But chapter 4 not actually difficult, like it's logic. It's not, chapter 3 is the one that is boring. Okay. So we have this 1, 2, 3, 4, 5, 6, 7, 8. Okay. So finish 1, 2, 3, 4, 5, 6, 7, 8. Mana Daniel? Tertidur ke? Aduh, saya cakap ni sebelum mau keluar. So I'm doing a hybrid actually now. Hopefully the internet's here. So today is radio digital modulation. So what does it mean? Means that previously we learned about analog modulation actually in chapter 2 and chapter 3. So where our information signal is actually analog as well. But this one, our information signal will be digital. Okay. So this one is actually extended version of chapter 4. Okay. Because chapter 4 only later we'll cover. Okay. This one is extension from the chapter 4. Okay. So this one is actually the block diagram of the entire part for the data communication system. Okay. You're not going to learn all of this. You only learn few parts of that because your major is biomedical, not communication. For me, I learn all of this. Okay. So there are three types technique that can be used. Okay. So it is pulse signals. We go to here first. Digital transmission. Pulse signal from the previous modulation or coding. Remember, we learned about sampling, quantization, and coding. Okay, now is the continuation part after that. Okay, pulse signal from the previous modulation or coding method. Okay, means previously, this one is chapter 4. Normally are not transmitted in their original baseband signal. So what does it mean by baseband signal is that when we transmit only the information, no carrier. Yes, can you turn off? Which one is it? I don't know. Is this okay? Thank you. So digital pass signal from the previous methods are not transmitted in their original form. Original form means we transmit purely the information. Okay, this what does it mean by baseband? Baseband signal. So if we tell you baseband signal means that kind of transmission is only purely information, which normally not we don't use lah. Okay. They will modulate a carrier that is suitable with the channel use. Okay, so if the channel is fiber optics, so we will use a carrier that is suitable with fiber optic transmission lah. Okay, if it's wireless, it's suitable with wireless lah. For example, 2.45 Wi-Fi, right? So 2.45 lah is the frequency lah. Okay. Digital signal can also be transmitted through the free space if the analog carrier is used. Okay, so there are three techniques that can be used: ASK, amplitude shifting, frequency shifting, and P phase shifting. This one is can be analogy to your AM, FM, and PM. This one actually. Okay. So amplitude shifting, frequency shifting, and phase shifting. So rather than listen to me only, which is I know quite boring, so I find one video. Maybe you can listen 3 minutes about ASK. This one is from the industry lah. Okay, how they explain Okay, Rhodes Schwartz is the electrical and electronic equipment measurement company. Okay, so they produce products that actually measuring this electronics. Okay, output. So last time when I was in industry, I am senior engineer of Keysight Technology, which is competitor of this company. Okay, so that's why I know about this company. So let's see, put this down. So you can learn 4 minutes. I try to maximize this one. And also this one, the sounds. Okay. Oh, open. Next time I don't want to buy Lenovo anymore. It's quite complicated. Others laptop just keluar. Lenovo you need to customize every time. Sound.
We'll explain the basic concepts behind amplitude. Welcome to this presentation.
Okay. But the laptop is good.
Hello, and welcome to this presentation, Understanding Amplitude Shift Keying.
Wait. Astaghfirullahaladzim, apa ni? Sorry. I'm so sorry. I didn't notice. You can see? Okay, so I will start again. This one is ASK.
Hello, and welcome to this presentation, Understanding Amplitude Shift Keying. In this short presentation, we'll explain the basic concepts behind amplitude shift keying, as well as give some examples of how this type of modulation is used in real-world applications. As the name implies, amplitude shift keying, or ASK, is used to encode digital data by varying the amplitude of an RF carrier. There are two general ways in which we can implement ASK. The oldest and easiest method is simply turning the carrier on and off, which is how Morse code is normally sent. The other method is varying the amplitude of a continuous carrier between two or more different levels, all of which are non-zero. An example of this is near-field communications, or NFC. Very few exceptions, amplitude shift keying involves two states. Technically, this could be referred to as binary amplitude shift keying, but you're unlikely to hear the specific term used since almost all applications of ASK use only two states. The on or on state is defined as 100% amplitude, and the 0 or off state is defined as a lower amplitude. As mentioned a few moments ago, the lower amplitude can be either 0 amplitude or some non-zero amplitude, as shown in the diagram here. The case in which we have a 0 lower amplitude is sometimes referred to as on-off keying, since we're essentially turning the carrier on and off. As shown by the graphs, a logical 1 is full amplitude, and a logical 0 is no amplitude. This is probably the easiest of all the forms of digital modulation. In traditional Morse code communications, the modulator is nothing more than a human hand. However, this transition between off and on states also has some potential disadvantages. It's more stressful for amplifiers and some other types of RF components, and the rapid rise and fall times can create undesired effects, such as spectral regrowth. One application that uses both types of amplitude shift keying is near-field communications. NFC specifies both variants for use in the uplink. NFC Type A uses on-off keying, or so-called 100% ASK, and NFC Types B and F use 10% ASK. All the examples of ASK that we've looked at so far show 2 levels, but it's possible to implement ASK with more than 2 levels. This is sometimes called M-ary ASK. For example, here we see the carrier taking on 4 different amplitude states. Each level corresponds to one of 4 different states, and each state can represent 2 bits. The use of more than 2 ASK states is, however, rather rare, largely due to the fact that noise can create more frequent bit errors as the number of amplitude states increases. So in summary, amplitude shift keying conveys digital information by changing the amplitude of the carrier in discrete steps. ASK is used in numerous applications, including Morse code, many types of wireless remotes, and NFC, or near-field communications. In almost all cases, ASK systems have 2 states: a high state that corresponds to 100% carrier amplitude, and a low state that is less than 100% amplitude. This lower state may be only slightly lower than full amplitude, or it may involve turning the carrier off completely, something called on-off keying. On-off keying is popular because it's very simple and inexpensive, but it can also lead to wider signal bandwidth or spectral regrowth, and complicates the selection and design of amplifiers. This concludes our presentation, Understanding ASK. Thanks for watching.
So ASK is basic. In whatever I watch. Okay. Okay, so if you see, ASK is just like similarly with AM, amplitude modulation. And it's just bit 1 is the higher one, 100%. Bit 0 can be 0 or lower. Means 5 volt is the higher bit 1. 4.5 can be bit 0. So doesn't mean bit 0 must be 0 volt. No, it's lower than bit 1. Okay, and it's easy to implement if we just we have on and off directly. Like a switch, off we just open, on we just connect. So that one is simple to implement, but they have shown just now, right? There is problem lah for amplifier even because suddenly you have value and suddenly you doesn't have value. Okay, so that is a disadvantage of having a ASK. So this is amplitude shift keying. So FSK, PSK actually also almost similar to FM and PM. Okay. Huh? She, I. I think that time I have. I think I say I have. That time I cannot access e-learning. I take. Okay. So this one is the Malay term. You're not going to use this. Okay. This one is Malay term for SK, amplitude shifting, pengujian ajakan amplitude. This one is Malay term for the FSK. This one is Malay term for the PSK. But luckily the short form here is in English, so you can actually relate. Okay. So this is if for bit 00, so you're going to have 0 stat. But doesn't necessarily 0, like what I told you, like what the video explained to you and I explained to you. So it can be still bit amplitude but smaller. Okay. But this one is the ideal one, 0, 1, 0. And the next one is FM. Okay. So for those that with bit 0, we're going to have lower frequency, and the one will with bit 1 will have higher frequency. Okay. So this is the modulating signal. Our modulating signal means our information signal is in terms of digital. So you highlight this one. So this is not carrier, this is your modulating signal. Okay. So this one is phase shift keying. So if you have 0 and if you have the next different of bit state, it's going to have phase shift. Do you see this? This one should be in continue. Wait, pen. Okay. Should continue. However, we have bit shift. It's look like this. If we have all around 0, 0. But if we have 0, 1, so this one, and should be continue down, but we have like this. Okay. So that's why you have this. That's why you have this one is just fold down. Okay. So that is phase shift. Uh, phase shifting. Okay. Angle. So next is this one is sorry, this one in English is digital channel. Okay. This one is analog channel. Okay. Ada lagi tak dalam bahasa? Sorry, I want to check if there is any in Malay. This one is modulator. This one is demodulator. Okay. Clear? This one is encode. This one is decode. Encode, decode, modulator, demodulator, modulation, demodulation. This one is analog channel. This one is digital channel. Okay. So here, like what you told just now, we learned digital data is used to modulate the carrier. Means our digital data is our information signal. Okay, which is our information signal MT. Okay. So we're going to study this. I think. Okay. So this BT is actually your modulating signal. BT. Okay. This one is encoding, where this one is like ADC, analog to digital converter, and so on. Then you will learn about digital signaling. Return 0, non-return to 0, AMI, Manchester, etc. This one you already learned in the previous chapter 4, right? Okay. I'm not sure you have watched the video, and also I give it quite late, so I kind of understand if you didn't watch. And also where is the Webex? I want to mute for a while. Kat benda tak boleh cakap. Okay. Okay. And I maximize again. Okay. Sorry. Okay. So if you see, so the task of the carrier is the same, to shift the baseband signal spectrum to a higher spectrum. So you know, right? Baseband spectrum, baseband signal is actually the information signal, so it's lower frequency. So the same job of the carrier in the AM FM. So the same job will be implemented in this. So actually to shift to the higher frequency. Spectrum is frequency, right? Spectrum is not time domain. Okay. Then here is the block diagram for digital transmission system. Okay. Of course, if you see the block diagram that I show you in the first picture, we have a lot of blocks. Okay. So this one is, of course, when you see this is not the entire block lah of communication system. Okay. It's just that we just show something that is relevant to this chapter only. So we have analog. Okay. Which is your information. Okay, and then you do this analog to digital converter. So this is where you get your in terms of coding lah. Okay, sampling, quantization, and coding. Okay, so this one of this actually come out in your test 2, right? Hint, uniform quantization. Am I correct? I put right. Okay. Then this is the line coding. Okay, line coding. So you have return 0, none return to 0, and alternate mark inversion. Okay. Then this chapter 5. Okay. Digital modulation. Why digital modulation? Because it's going to be modulated by digital signal, which is our information signal in terms of digital. Okay. So ASK, FSK, PSK. Oh, okay. In my previous class signal, around 11 to 1, that class is like hell because only one aircon working. This class is just like the opposite. All aircon working and the student is too little. Okay. So this one is ampli. Wait, I want to check my recording because I need to wait. Dah record tak ni? Record and unmute. Okay, good. Okay. So this one it been explained by the video just now. It's just that the video didn't touch on this. Okay. So if you see this is your carrier. Okay? And this is your signal. Okay. Your information signal. Okay. Which is, of course, if you see information, it is as the lower spectrum, right? And then modulate with your carrier. So you will shift the entire information signal to higher frequency UWC. And the rest is just a minus or plus with respect to the information signals. Okay. So this one has been explained by the videos. Okay, on and off. Okay. So this one is actually what happened in AM lah. So by now AM, that's the relevant why we teach AM. Actually AM is not relevant anymore, but we still teach because it's the basic. Otherwise, difficult for you to learn FM and the rest. So ASK signal generation. Okay, this one is to generate the ASK. So you have the information signals in terms of this digital, which is like rectangular. Okay, so then modulate with mix with this VC, your carrier, then you get the amplitude shift keying. So this one you learn from signal and system. That's why you must pass signal and system before coming to this class. Okay, so this one is the Fourier one. Fourier series, right? Fourier transform is for non-periodic. Fourier series is for periodic. Okay. So I'm quite lucky this semester I teach both signal and pre-com. Okay. Together. So VMT is half of this. This is actually coming from your signal and system. Okay. Fourier series. Okay. So it doesn't just exist here. It doesn't just exist here. It's actually have value. This you learn from senior system. We'll not cover here because otherwise we don't have time. So VCT equals to EC cos omega C, where omega C much higher than omega M. Cannot only higher, but much higher. They say this is 2 to the power of 3. This one maybe can be 2 to the power of 6. Okay. So therefore, this one is just multiply. Then you will get EC cos omega C and the rest of this. Okay. Let's say we say until 7 harmonics means you're going to have cos 7 okay, omega mt. Okay, depends on how many harmonics is being asked, and depends on also the shape. I'm not sure if they only give this rectangular, but so far the slide is using rectangular. But can we change to triangle? If you want, can I? If I want to change to triangle, also can. Okay, but don't worry lah. I think no triangle. I'm not sure. Okay. It's just that this is for learning purpose. We go to basic one because I think we also don't want to ask many. But you shouldn't assume it's always like this. Okay. So depending on the receiver requirement on square shaping, okay, the square shaping, if only the first 5 harmonic are considered, means until 5 harmonics. Harmonics you learn in signal, and system is just the multiple of the frequency. So 1F, 2F, 3F, 4F, 5F. 5F is 5 harmonics. So this one is bit rate. Okay. 2 FM equals to 2 FM. And if only 5th harmonic are considered, mean until 5 harmonics. So bandwidth is actually equals to 5B. If only 5 harmonic, 5 FB. And FB is equals to 2 FM. So it will be how much? It will be 10 FM. If 5th harmonics. So means your bandwidth is depend on how many harmonics. Okay. So this is basically the bandwidth of your ASK. Okay. Amplitude shifting. And this one is the word here, foreigner, sorry. This one means SK spectrum envelope. SK spectrum envelope. This one is carrier signal. This one means carrier signal. Oh, tak nampak Cannot see. Sorry. This is the biggest I can go. So see on your slide. So this one is carrier signal. This one is ASK spectrum envelope. This one is ASK signal. This one is data signal. Okay. I direct translate hopefully it's correct Okay. So this one is power spectrum density omega over hertz. Okay. So when we say about power, so it's watt. However, the word here power spectrum density. So we must have a factor of hertz inside. So that's why omega over hertz. Okay, like density lah. So this is basically the amplitude. And I think you learn this as well actually from your signals. So this is your input signal, which is your modulating signal. So you have 2T, okay, the complete periods. So SK generation, and this one is ASK receiver. So means this one is at the generation side, and this one is at receiver side. So anyway, since you don't have this in test 2, so you're going to have this purely in final exam. So which I assume logically it should be challenging lah, because it's inside the final exam. Okay. So using multipliers, this one is your VMT. Okay. Rectangular signal. So depends if it's unipolar. Okay. So you're going to have 1, 0. I mean, This one is already coding lah to 10. If in the previous chapter 4, you just see the video, there's a term unipolar bipolar. Okay. So VMT